Imagine you're in the fastest spaceship ever built, accelerating harder and harder, pushing closer and closer to the speed of light. Your engines are roaring, fuel is burning, you're going faster than anything humanity has ever created. But here's the thing that'll blow your mind. No matter how much fuel you burn, no matter how powerful your engines are, you will never, ever reach the speed of light. And it's not because we haven't built good enough technology yet. It's because the universe itself has a speed limit written into the fabric of reality, and breaking it isn't just impossible with our current tech, it's impossible, period. The laws of physics literally won't allow it. But why? What makes light so special? And what would actually happen if you tried? Stay with me, because what you're about to discover will completely change how you see reality itself. Before we dive deeper into this cosmic mystery, do me a favor and hit that subscribe button and turn on notifications. Trust me, Physics Decoded is about to take you on a journey that'll make you see the universe in a completely different way, and you don't want to miss what's coming next. So let's start with something that seems simple but actually reveals something profound about our universe. When you're driving your car and you press the accelerator, you speed up, press harder, go faster. That makes sense, right? And in our everyday world, there doesn't seem to be any ultimate limit. If you could keep adding more and more energy, you'd just keep going faster and faster forever. At least, that's what Isaac Newton thought, and for over 200 years, that's what everyone believed. But then came Albert Einstein, a 26-year-old patent clerk working in Switzerland, who asked a question that would shatter everything we thought we knew. He asked, what would happen if you were traveling at the speed of light and you looked at yourself in a mirror? According to the old physics, the light leaving your face would be frozen in place relative to you, which means you wouldn't see your reflection. But Maxwell's equations of electromagnetism said light always travels at the same speed, no matter what. These two ideas couldn't both be true. Einstein realized something shocking. The problem wasn't with the math. The problem was with our assumptions about reality itself. We'd been wrong about something so fundamental, so basic, that it had never even occurred to anyone to question it. We'd been wrong about time and space. Here's where things get wild. Einstein discovered that time and space aren't separate, fixed things. They're connected, woven together into what we call spacetime, and they're flexible. They bend and stretch depending on how fast you're moving. When you move faster, time literally slows down for you compared to someone standing still, and distances contract, becoming shorter in the direction you're traveling. This isn't science fiction or some weird theoretical idea. This is measurable, testable, proven reality. Scientists have actually tested this with atomic clocks on airplanes. They took two incredibly precise atomic clocks, synchronized them perfectly, then flew one around the world on a plane while the other stayed on the ground. When they brought them back together, the clock that had been flying was behind the one that stayed still. Not by much, just a few billionths of a second, but enough to prove the point. Time had literally moved slower for the clock in motion. We've also seen this in particle accelerators, where subatomic particles moving at nearly the speed of light live significantly longer than they should, because from their perspective, time is passing more slowly. But here's where Einstein's discovery gets even stranger. These effects, time slowing down and distances contracting, become more and more extreme as you approach the speed of light. And there's something else that happens too, something that creates an absolute barrier nothing can cross. Your mass increases. Now, when I say mass increases, I don't mean you get fatter or heavier in the normal sense. What I mean is that your resistance to acceleration increases. Think of it this way. The faster you go, the harder it becomes to go even faster. It's like you're pushing through an increasingly thick substance, and the closer you get to light speed, the thicker it gets. When you're moving at 90% the speed of light, your effective mass has more than doubled. At 99%, it's increased by a factor of 7. At 99.9%, it's more than 20 times your rest mass. This is where Einstein's most famous equation comes in, E equals mc squared. Energy equals mass times the speed of light squared. What this equation tells us is that mass and energy are the same thing, just in different forms. When you add energy to something to make it go faster, you're not just increasing its speed, you're increasing its mass. And here's the kicker. As you approach the speed of light, the amount of energy needed to accelerate you further approaches infinity. Let me put that in perspective. Imagine you're in a spaceship, and you're already traveling at 99.9% of light speed. To accelerate just a tiny bit more, to 99.91% would require an enormous amount of energy. To get to 99.99% would require exponentially more, and to actually reach 100%, to reach the speed of light itself, would require infinite energy, not just a lot of energy, not more energy than exists in all the stars in the universe, literally infinite energy. And since infinite energy doesn't exist, you can never get there. This is the cosmic speed limit. It's not a suggestion or a challenge to be overcome with better technology. It's a fundamental property of spacetime itself. The speed of light isn't just the speed that light happens to travel at. It's the speed that causality itself propagates through the universe. It's the speed at which cause and effect move through spacetime. But here is something that might surprise you. Light doesn't actually travel at the speed of light because it is trying really hard. Light travels at the speed of light because it has no choice. Photons, the particles that make up light, have zero mass, and anything with zero mass must travel at the speed of light. It can't go slower, and it obviously can't go faster. This is why light from the sun doesn't gradually slow down on its journey to Earth. It's locked at that speed by the structure of the universe itself. And here's another mind-bending fact. From the perspective of a photon, no time passes at all. If you could somehow ride along with a beam of light traveling from a distant galaxy to your eye, the entire journey, which might take billions of years from our perspective, would be instantaneous from the photon's perspective. The photon is emitted and absorbed in the same moment, with no time in between. This is what happens when time dilation becomes complete. When you're moving at the actual speed of light, time stops entirely. Now, you might be thinking, okay, maybe we can't reach the speed of light, but what about finding a loophole? What about going around the rule instead of through it? This is where things get really interesting, because physicists have actually found some theoretical loopholes, and they're absolutely fascinating. The first one involves something called wormholes. Now, Einstein's equations don't just predict that spacetime can bend, they predict it can fold, creating shortcuts through the universe. Imagine spacetime as a sheet of paper. Normally, to get from one point to another, you'd have to travel across the surface. But what if you could fold the paper so the 2 points touch and then punch a hole through? That's essentially what a wormhole is. A tunnel through spacetime that could potentially let you travel vast distances without actually moving faster than light through space. The catch: we have no idea if wormholes actually exist, and even if they do, they'd probably be incredibly unstable. Most calculations suggest they decollapse immediately unless you could somehow prop them open with some kind of exotic matter with negative energy, which we've never seen and aren't sure even exists. Plus, some solutions to Einstein's equations suggest that wormholes might allow time travel to the past, which opens up a whole can of worms involving paradoxes. Kill your grandfather before he meets your grandmother, and you were never born. But then you couldn't have gone back to kill him, so you were born. So you did go back. You get the idea. Then there's the Alcubierre drive, named after physicist Miguel Alcubierre, who proposed it in the 1990s. This is probably the closest thing to a realistic faster-than-light travel method that doesn't violate Einstein's rules. The idea is brilliant in its simplicity. You don't move through space at all. Instead, you compress the space in front of you and expand the space behind you, creating a wave of space-time that carries you along. You're sitting inside a bubble, completely stationary relative to the space around you, but the bubble itself is moving faster than light. It's like standing on a moving walkway at the airport. You're not walking any faster, but you're getting to your gate quicker because the floor is moving under you. With an Alcubierre drive, space-time itself is the moving walkway. From the outside, you'd appear to be moving faster than light, but from your perspective, inside the bubble, you're not moving at all. You're not breaking Einstein's speed limit because you're never actually moving through space faster than light. Space itself is moving. Sounds perfect, right? Well, not quite. First problem: it requires negative energy, that same exotic matter we'd need for wormholes. Second problem: the amount of energy required would be absolutely astronomical, possibly more than the total mass energy of the observable universe. Third problem: you might not be able to control or steer it once you're inside. Fourth problem: some calculations suggest that when you turn off the drive and arrive at your destination, you'd release a burst of deadly radiation that would destroy everything in front of you. So you might get to Alpha Centauri, but you'd annihilate it in the process. But here's what's truly fascinating about both of these ideas: they don't violate relativity. Einstein's equations don't say space itself can't move faster than light. They say objects with mass can't move through space faster than light. There's a difference. In fact, space itself is expanding, and distant galaxies are moving away from us faster than light right now because of the expansion of the universe. We can never catch up to them or send signals to them because they're receding faster than light can travel. But it's not the galaxies moving through space that fast. It's the space between us and them that's expanding. This brings up another crucial point about the speed of light limit. There's really a limit on information transfer. You can't send a signal, a message, or any kind of cause-and effect interaction faster than light. And this is crucial for maintaining causality in the universe. If you could send information faster than light, you could, under certain circumstances, send information backward in time, and that would break causality, the fundamental principle that effects follow causes. Let me explain why. Imagine you're in a spaceship moving away from Earth at high speed. Because of relativity, your perception of what's happening now on Earth is different from what someone on Earth thinks is happening now. Events that appear simultaneous to you happen at different times for someone else. Now, if you could send a faster-than-light signal from your spaceship to Earth, you could exploit this relativity of simultaneity to send a message that arrives before it was sent from Earth's perspective. You could essentially send a message to the past. This is why causality and the speed of light limit are so deeply connected. The universe doesn't just prohibit faster-than-light travel because it's difficult. It prohibits it because allowing it would break the logical structure of reality itself. Effects could precede causes. You could receive an answer before you asked the question. The timeline of events would become scrambled and paradoxical. Some physicists have wondered, what if there are particles that naturally travel faster than light? These hypothetical particles are called tachyons. If they exist, they'd be really weird. They'd have imaginary mass, whatever that means, and they'd speed up when they lose energy instead of slowing down. Most importantly, they'd always have been traveling faster than light. They couldn't slow down to light speed any more than we could speed up to it. But here's the thing. We've never detected a tachyon ever, despite decades of looking, and most physicists think tachyons don't exist because they decreate all sorts of paradoxes and violations of causality. If they existed, the universe would be a very different, much weirder place than what we observe. So where does all this leave us? Why did the universe set this limit? Why is the speed of light what it is and not something else? These questions get at something profound. The speed of light, which is about 299,792,458 meters per second, or about 186,282 miles per second, isn't just a random number. It's woven into the fundamental constants of nature. It appears in equations describing electromagnetism, gravity, quantum mechanics, and the structure of spacetime itself. Some physicists think the speed of light is related to the fundamental structure of spacetime at the smallest scales, the Planck length and Planck time. These are the smallest possible meaningful units of space and time, so small that our current physics breaks down. The Planck length is about 10 to the negative 35 meters, which is to an atom what an atom is to the entire observable universe. At that scale, spacetime itself might be grainy or foamy, and the speed of light might emerge from this fundamental graininess. But honestly, we don't fully know why the speed of light is what it is. It's one of those fundamental parameters of reality that just seems to be what it is. In a different universe, with different fundamental constants, the speed limit might be different, or there might not be a speed limit at all, though such a universe would probably be so different from ours that it is hard to imagine what it would be like. What we do know is that the speed limit has shaped everything about our universe. It determines how fast information can spread, how quickly forces can act, and ultimately, what kinds of structures and patterns can exist. Without it, the universe would be a very different place. Stars might not be able to form, atoms might not be stable, causality might not exist in any meaningful way. For us humans, stuck in our small corner of space on this little planet, the cosmic speed limit is both frustrating and awe-inspiring. It means that even if we develop incredible technology, we're fundamentally limited in how quickly we can explore the universe. The nearest star system, Alpha Centauri, is over 4 light-years away. Even if we could travel at 99% of light speed, which is nowhere near possible with current technology, it would take over 4 years to get there. The center of our galaxy is about 27,000 light-years away. The nearest large galaxy, Andromeda, is about 2.5 million light-years away. These distances are so vast that they're almost incomprehensible. Light from Andromeda that reaches your eyes tonight has been traveling through empty space for 2.5 million years. When that light began its journey, our human ancestors were just learning to use stone tools. The universe is telling us something profound. You are here, and there's a fundamental limit to how quickly you can get from here to there. Distance and time are real, and they matter. But here is a thought that might give you some comfort. While the speed limit prevents us from easily exploring the universe, it also protects us. If faster-than-light travel were possible, causality would be violated, and the universe might not be comprehensible or predictable. The laws of physics might not be laws at all. The speed limit is part of what makes the universe orderly, what makes it possible for structures like stars and planets and life to exist in the first place. And who knows what the future holds? While we can't break the laws of physics, we keep discovering new things about how the universe works. Maybe we'll find a way to manipulate spacetime in ways we can't currently imagine. Maybe we'll discover that the universe has extra dimensions we can exploit to create shortcuts. Maybe we'll develop technology that lets us send consciousness or information in ways that get around the physical limitations. Or maybe we'll discover that the journey, not the destination, is what matters. That exploring our own solar system and learning everything we can about our cosmic neighborhood is adventure enough for now. The speed of light limit isn't a failure of human engineering or a challenge to be overcome. It's a fundamental feature of reality, as basic as the fact that 2 + 2 = 4. Understanding this, really grasping what it means, is one of the great achievements of human thought. We live in a universe with rules, and those rules are written into the fabric of spacetime itself. The cosmic speed limit is one of those rules, and respecting it means respecting reality itself. So the next time you look up at the stars and wonder what's out there, remember that you're looking backward in time. The light entering your eyes left those stars years, decades, centuries, or even millennia ago. You're seeing the universe, not as it is, but as it was. And that's because of the speed limit, the cosmic constant that shapes everything about our reality. We can't travel faster than light, but we can understand why. And in that understanding, we glimpse something profound about the nature of the universe itself. Now I want to hear from you. What do you think about the cosmic speed limit? Does it frustrate you that we're essentially trapped by the laws of physics? Or do you find something beautiful about living in a universe with fundamental rules? Drop your thoughts in the comments below. I read every single one, and some of the best discussions happen down there. And if this video made you see reality a little differently, do me a huge favor, share it with someone who loves thinking about the big questions. Hit that share button and spread the knowledge. The more people we get thinking about the fundamental nature of reality, the better conversations we can all have. Thanks for sticking with me through this journey into the heart of physics. If you loved this deep dive, you're going to love what's coming next on Physics Decoded. We're going to explore even more mind-bending questions about the universe, so make sure you're subscribed with notifications on. I'll see you in the next video, where we'll decode even more of the mysteries hiding in plain sight all around us. Until then, keep questioning, keep wondering, and keep looking up at those stars.